Testing. Testing, testing. Testing, 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 testing. Testing, testing. Alright, this works. How's it going, everybody? How's it going, Joseph? How's it going, Christopher? How's it going, Ed? We're going deep today. You guys better be ready. We're going straight into the quantum realm over here. So today we're going to be reading a paper. It's not necessarily a new paper, but I wasn't trying to pick the most recent quantum machine learning paper. I just kind of wanted to pick a quantum machine learning paper that was a little bit approachable, and maybe I can build a little bit better intuition. Right? So obviously the caveat here is I am not a quantum machine learning expert at all. I'm going to basically have to constantly ask these AIs and go on the internet and find definitions for terms that I don't understand. But that's kind of the point, right? And that's kind of why I chose this paper. This is a paper that was recommended by someone on the Discord. And it's basically someone implemented self-attention, which is one of the kind of basic components of transformers, which are the super popular architecture nowadays. But they implemented it in quantum world. So hopefully, because I know what all of these words mean, I should eventually figure out what that word means. And that's the whole point. So neural networks are just neural networks, networks of neurons. Self-attention neural networks are specifically a architecture module that is repeated many, many times inside neural networks. And text classification is just classifying text. So given some amount of text, classify it as, I don't know, maybe a basic example would be sentiment prediction, sentiment analysis. So is this text mostly positive or mostly negative? But, all right, this is coming from Baidu Research Institute for Quantum Computing in China, and then Center for Quantum Software Information, which is in Sydney in Australia. So let's see. An emerging direction of quantum computing is to establish meaningful quantum applications in various fields of artificial intelligence, including natural language processing. Although some efforts based on syntactic analysis have opened the door to research in quantum NLP. Okay, analysis of syntax, maybe? I don't know if that has a special definition in the quantum world, but quantum NLP is called QNLP. Limitations such as heavy syntactic pre-processing and syntax-dependent network architecture make them impracticable. Isn't that supposed to be impracticable? Is this a fucking real word? On larger and real-world datasets. Maybe what they mean here by heavy syntactic pre-processing is tokenization or dataset cleaning. In this paper, we propose a new simple network architecture called quantum self-attention neural network. So, all right, it's simple, so hopefully we should be able to understand this. We introduce the self-attention mechanism to quantum neural networks and then utilize a Gaussian projected self-attention serving as a sensible quantum version of self-attention. Okay, so this is really what we're hoping to get out of this paper is how would you implement self-attention with qubits? QSAN is effective and scalable on larger data sets. Okay, so that's probably important. Most of the intelligence that you're getting is not coming from the architecture itself. The architecture is just a generic function approximator that can find a function, but really what your intelligence is coming from is from the data set. So if you can't feed large data sets through this thing, it's not going to learn anything useful. Has the desirable property of being implementable on near-term quantum devices. Okay, so I think what they mean here is that within the field of quantum machine learning, there's people who do research, but they do research on quantum devices that don't even exist yet. So they have basically these theoretical, what a quantum computer would look like 100 years from now, and then let's design an algorithm for that quantum computer 100 years from now. Versus I think this paper is going to be a little bit more application focused and kind of say, okay, well, what do we actually have right now? And can we implement it on that? So that's what they mean by near-term quantum devices. Gaussians and qubits. Why didn't I come up with this? Everything is just Gaussians, which is, I guess, what Bayesians want to think about. Our QSAN outperforms the best existing QNLP model. I don't think there's a huge amount of competition for this, so that's probably not super impressive. Based on syntactic analysis as well as simple classical self-attention neural network in numerical experiments of text classification tasks on public datasets. Interesting. So they say it beats simple classical neural networks. Classical here just means using traditional computers, which are 0 and 1s, right? This binary system that kind of underpins all of our computation right now. Numerical experiments of text classification on public datasets. And we further show that our method exhibits robustness to low-level quantum noises. So I think what they mean here is that at the end of the day, quantum computing is all about a computer where the underlying state is not 1 or 0, but it's a superposition of those. It can basically exist in anywhere between 0 and 1, so kind of like an infinite possible set of values. But when you're dealing with an actual quantum computer in the real world, if there's anything in the outside world that even just ever so slightly disturbs one of the qubits, then that noise is going to propagate through the entire quantum system, and you might get a nonsense answer at the end. So it would make sense that if you're trying to design any kind of algorithm that is going to work in a quantum computer, you need it to be somewhat robust to the noise that could be introduced there. That's my guess as to what low-level quantum noise is. All right, so now that I've lost about 90% of you guys, let's go deeper. Quantum computing is a promising paradigm for fast computations that can provide substantial advantages in solving valuable problems. All right, kind of meaningless there. Major academic, developing quantum algorithms on quantum hardware led to an increase in number of powerful applications such as optimization, cryptography, chemistry, and machine learning. That's the one that we're interested in right there. Quantum devices, currently known as the noisy intermediate scale quantum devices, have up to a few hundred physical qubits. So why don't we get good old ChatGPT to explain this to us. Explain quantum or noisy intermediate scale quantum devices. They are affected by coherent and incoherent noise. I don't know what the definition of coherent versus incoherent noise is, making the practical implementation of many advantageous quantum algorithms less feasible. Yeah, so if your quantum algorithm is sensitive to noise, it's just going to be garbage. Such devices with 50 to 100 qubits already allow one to achieve maximum quantum advantage against the most powerful classical computers on certain carefully designed tasks. And this is I think a couple years ago, there was a Google kind of release where they said we've achieved quantum supremacy. And this is kind of what they meant, is that there's some specific algorithms where they were able to show that with a much smaller quantum computer compared to the total amount of classical compute, you would basically be able to solve it better with the quantum computer with just 50 to 100 qubits. So maybe there's a Moore's law for qubits. I doubt that there is. Is there a Moore's law for qubits? Moore's law for qubits. If there isn't, there's probably going to be one pretty soon. To double the power, you just add 1 qubit. Therefore, to keep pace, quantum machines need only to grow by 1 qubit every 2 years. That seems pretty feasible. Let's see. Oh my god, these pictures are trash. Okay. So Moore's law famously is the amount of transistors that you can fit. And there are some people that say it's no longer applicable, but it largely has remained applicable. And here we actually see that the quantum volume, which is probably not exactly the number of qubits, but something that is proportional to that, has been increasing. So we see here over the years it has been going up, and actually this last uptick is quite impressive here. We went from 64 to 128. I guess maybe that's just one extra qubit, but okay, if we can expect a Moore's law in quantum computers, then we should see computers with many more qubits soon. All right, while we were talking, GPT gave us a little summary here of noisy intermediate scale quantum devices. Let's see. Class of quantum devices that are available in the era prior to full error correction in quantum computers. Okay, so prior to full error correction, so maybe there's a whole branch of quantum computing that is kind of assuming that at some point we're going to get to full error correction. So right now we're living in the era prior to that. More qubits than small proof of concept. The term intermediate scale refers to machines with tens to a few hundreds. Okay, so that's what the intermediate basically means. Noisy, those from external environment, right? So this is why they keep them in these very, very sensitive boxes that are super cooled and in these rooms that are vibration proof and everything, right? Because they don't want any external stray photon coming in and just interfering with the quantum state of a qubit. Cannot entirely eliminate these errors and do not yet employ full quantum correction. I wonder if you could think of the limited, right? Our computers right now cannot represent a floating point number perfectly. They're approximating it to some precision, which is determined by the data type, right? So you could say that every single parameter in a neural net right now has some noise in it because we don't actually know the exact value of that weight, right? We are approximating it with some float that only has a limited amount of precision. So I wonder if there's kind of an analogous thing going on here where the noise is very low magnitude. Let's see. Practical short algorithms. Due to the noise, quantum algorithms run need to be shallow, meaning they can't have too many consecutive operations. Okay. So it makes sense. Your noise is going to propagate, so you can't have them be very deep. You can't have many successive computations. That's not necessarily great because deep learning is deep, right? You have many, many layers, and the output of one layer is fed to the next layer, and then fed to the next layer, and then fed to the next layer. So if you have an error at the very beginning, you're kind of screwing yourself. But maybe if the noise is small enough, it doesn't matter. Algorithms like quantum approximation optimization use both quantum and classical components to solve problems. Okay, so there's like hybrid quantum and classical components. NISQ are of considerable interest. They allow for testing even before full-scale error-corrected quantum computers become a reality. Okay, so we haven't gotten to this point yet. All right, so I kind of have an idea about what a noisy intermediate scale quantum device is. It basically just means a quantum computer that exists in today's world. It's got a couple hundred qubits at max, and it has some noise, unfortunately. Okay. In particular, those algorithms dealing with machine learning problems by employing parameterized quantum circuits, so quantum circuit that has some parameters, also called a quantum neural network. Okay, so the same way that I guess a neural network is a circuit because you have a bunch of neurons and then those neurons have a specific connectivity to them, and each of those neurons has a parameter that is the weight. So I think I understand what those words mean now. Great potential in the field of quantum machine learning. However, in artificial intelligence, the study of QML in the NISQ era is still in its infancy. Yeah, and this is kind of why I'm starting to be more interested in this, because I think that quantum computers were 10 years away, but I don't know if they're 10 years away anymore. I think they're more like 5 years away, or potentially even 3 years away, right? If the LK99 would have been not a dud, we would have gotten quantum computers quite quickly. So unfortunately, the LK99 is probably not correct, and it's not necessarily a room state ambient or room temperature ambient pressure superconductor, but I still feel like there's going to be breakthroughs, and as soon as we have quantum computers, then we're going to all have to learn how to do quantum machine learning, because the entire field is going to very quickly switch to those computers because they're just much better. It is desirable to explore QML algorithms exploiting the power that lies within these devices. Okay, NLP. It's going to be a little summary of NLP here, but basically you have speech recognition, translation, text classification, etc., blah, blah, blah. Natural to think about whether a quantum computer can enhance performance in this. Another approach, known as quantum natural language processing, seems to develop quantum native NLP models implemented on quantum devices. Though at the frontier, lack scalability, and they're based on syntactic analysis, which is a pre-processing task requiring significant effort. Okay. Syntax-based methods employ different PQCs, these parameterized quantum circuits. What happened with the room temperature superconductor? Has no one been able to reproduce it? I think a lot of people have had trouble reproducing it. So as far as we know, it might not. I don't think they lied. I think it's probably, so based on what I've been reading, they probably created something that they don't exactly know what it is. So they had some theory where they were basically saying, okay, there's copper atoms and then there's lead atoms, and that's why it's a superconductor. But people have recreated that, and it's not a superconductor. So I think maybe the sample that they created, and apparently according to the story, the two people who worked on this, they created thousands of samples, and only one of them was superconducting. So it makes sense that if people are trying to replicate it, they're not going to get it on the first try, right? They're probably going to have to try thousands of times, and then eventually they'll figure out, oh, okay, this is actually why it's superconducting, and actually because of that, we need to manufacture it completely differently than the authors in the paper said. But LK99 in the exact form described in the paper is not a superconductor. We need to do more research. What else? Overcome these drawbacks, we propose quantum self-attention, okay, where the self-attention mechanism is introduced into a quantum neural network. Our motivation comes from the excellent performance of self-attention on various NLP tasks. So maybe one thing that they're not talking about here is that the reason self-attention is so good is because it can be parallelized, right? Because you can basically use the query and value. So self-attention relies on basically these three matrices, which are the keys, queries, and values. But the magic of the self-attention is not that it's doing something that is magic, right? The magic is that you can actually parallelize it on a GPU, and it actually allows you to process a huge amount of data through it. So maybe replicating self-attention in quantum circuits is not necessarily exactly the direction we want to go to, right? Maybe we want to figure out a quantum native model that'll work much better. I don't even know if people parallelize things in quantum computers. I don't know if that even makes sense. Kind of fishy they don't hand out the sample. Yeah, I think it's because the sample that they got is actually a piece of alien technology. That's my secret conspiracy theory, is that they know this sample is not created by humans. It was created by aliens, and the U.S. government gave it to them, and then that's why they released it the day of the congressional hearings on aliens, because they were like, we're not going to get sued for this if we release this. We're just in Korea here, like nobody's going to care. So they release it, and then they have some idea of what the thing is, but they don't actually know how to create it, right? Okay, conspiracy hat coming off, and let's go back into this quantum world. Note that a recently proposed method for quantum state tomography is an important task in quantum computing, adopts the self-attention mechanism, and achieves decent results. Christopher, you're not convinced that it's a piece of alien spaceship. Yeah, the rabbit hole goes deep. Okay, so quantum self-attention layer, we first encode the inputs into high-dimensional quantum states. Okay, so the inputs are going to be natural language, so they're going to have to be classical inputs, right? So you're going to have to figure out how to take these classical inputs, which is these either text tokens or the raw text itself or something like that, and encode it into an actual quantum computer. So how are they going to do that? They're going to apply these quantum circuits on them according to the layout of the self-attention neural networks and finally adopt a Gaussian projected quantum self-attention. Okay, so this is maybe the full name of their exact module. To obtain the output effectively. To evaluate performance, we conduct numerical experiments and blah, blah, blah. We show that QSAN outperforms the currently best known QNLP model and so on. Okay. So here's the contributions of this paper, nicely listed in a bullet format at the end of the introduction. You love to see that. Our first proposal is the first QNLP algorithm with a detailed circuit implementation scheme based on self-attention mechanism. You know what? This is probably a little bit small for you guys. Why don't I do this? Oh no. Let me make it big because I can see this because I have a big monitor, but you guys can't. So let me make this a little bit bigger. I gotta ask my friend Kim on LinkedIn. Are you talking about the leader of North Korea? Do you think the leader of North Korea knows about the aliens? Our proposal is the first QNLP algorithm with a detailed circuit implementation scheme based on the self-attention. This method can be implemented on NISQ devices and is more practicable on large datasets compared to previously known QNLP methods. Okay, so large datasets, practicable on large datasets. I don't know what practicable means here. I guess it just means it works, but it probably still takes a ton of time to feed a huge text corpus into one of these NISQ devices. Introduce a Gaussian projected quantum self-attention, which can efficiently dig out the correlations between words in high-dimensional quantum feature space. Right, so the whole point of quantum qubits is that you're not as limited as classical computers, where basically you to represent anything you're limited by, you have to represent, it has to boil down to zeros and ones. So your embeddings and features are fundamentally going to be limited by that, versus in a quantum computer you can have much higher dimensional feature spaces. Furthermore, visualization of self-attention coefficients on text classification confirms its ability to focus on more relevant words. Okay, so they're going to be doing some kind of saliency to see exactly what words are being paid attention to. We experimentally demonstrate outperforms existing methods. And several public data sets. Okay, so then they're going to basically show that it works on some generic text classification. All right, and now we're going to go, this is where it starts getting a little hairy. And they're going to give us, in the preliminaries and notations section here, a summary of quantum computing. Here are some basic concepts about quantum computing. All right, so in quantum computing, quantum information is usually represented by an n qubit. So we have n total bit qubits, right? And we know that that's roughly in the order of 100 over Hilbert space. So Hilbert space, right? You've seen perhaps the fancy script R, which means real numbers, right? This is just C is the Hilbert space, and Hilbert space, you can see that the dimensionality of it is 2 to the n. So if you have 1 qubit, it's 2. If you have 2 qubits, it's 2 to the 2, right, which is 4. And then if you have 3 qubits, it's 2 to the 3, which is 8. So you can see how as you increase the number of qubits, the dimensionality of this Hilbert space grows very, very fast, right? Because it's 2 to the power of the number of qubits. So, because I don't know enough about Hilbert spaces to actually accurately give you guys a good, satisfying definition, why don't we ask GPT here, explain Hilbert space in the context of quantum computing. And why don't we also ask Claude, let's do a new one here, and then let's ask Bard. Let's refresh, paste, enter. Quantum systems are described by quantum states, a single quantum bit. This state can be thought of as a vector. Okay, so Hilbert space is a vector space that is equipped with an inner product. Inner product allows for the calculation of angles or lengths. Inner product is basically the dot product, and then the outer product is the matrix multiply. So here is a quantum state. So this is what they're talking about when they say a single qubit is a vector. So a qubit isn't 0 and it isn't 1, right? It's actually both of those at the same time. So it's some superposition of those two, which means that it's some amount of 0 and then some amount of 1, right? It's kind of in between those two. So there's two numbers here that'll tell you what that state is. So that's why it's a vector. This state lives in a two-dimensional Hilbert space. For multi-qubit systems, the two qubits have a basis states. So you can think of these as the basis vectors are 0, 0, 0, 1, 1, 0, and 1, 1. Okay. The inner product allows us to define orthogonality between states. For instance, 0 and 1 are orthogonal. And this notation here, this is called bra and ket notation. I should actually, bra ket notation. This comes from physics. Comes from Dirac, Paul Dirac. This is the way that he wrote vectors, but they're basically just vectors. Let me see if I can find a nice, these suck. This is a terrible description. Sometimes Wikipedia has absolute shit tier explanations. University of Nevada. It's called a ket. So this is the ket, and then the opposite one is the bra, and the bra is usually the conjugate of the ket. Represents a complex number that's valued the inner product. So whenever you see like this, like that means alpha times b inner product, so the dot product between those. And then this is the outer product. So this will create a matrix. Is there anything else? I feel like this is still crap. Images. Let me see if there's good images here. Maybe this. Cat equals this. All right, perfectly. Actually, this might be a meme, but this is a pretty good image, right? So the quantum state of the cat is some combination of the cat being alive and the cat being dead, right? This is a reference to the Schrodinger's cat, which is both alive and dead, right? So the cat is neither alive nor dead. It's some combination of those two. It's kind of a good little thing there. Okay. What else? When a measurement is performed, it collapses into one of the basis states. Okay, so that's another important part, is that when you're using a quantum computer, you can perform a bunch of computations, but then at some point, if you actually want to measure it, it's going to collapse the entire state, and you're going to lose all that information that you had that was just kind of floating around in the fact that the probabilities, that it was a kind of a superposition. So as soon as you measure it, it's no longer a superposition, and you lose all the information, which is kind of a problem if you're going from classical inputs and you want ultimately classical outputs of like, what is this text? Quantum states can become entangled, meaning the state of one qubit cannot be described independently of another. Entangled states also exist in Hilbert space, reflecting the complexity of the quantum system as a whole. Okay. Hilbert space provides the mathematical framework to describe and manipulate quantum states. Let's see if Claude gives us a better definition here. Allow for inner products between vectors, giving a measure of angles and distances. So very similar to the dot product, right? The dot product is kind of telling you the angle between two vectors. It's not quite, because what does it mean by here by distances? Distance is the angle. Provide a framework for representing linear operators that can act on a quantum state. Capture the probabilistic nature, since vectors can represent quantum superpositions. Qubits are represented as state vectors in a two-dimensional Hilbert space called a block sphere. Right, shit, dude, it sucks whenever they introduce new things like that. Okay. So I'm kind of getting repeatably similar things, you know? It's dangerous to use these AIs whenever you don't exactly know, right? It's like, I don't know enough about quantum computing to like know how much of this is hallucinated, but I tend to be of the opinion that if you kind of look at all three of these answers, the things that are the same between all of them are probably true. Can be in two states, 0 and 1, so then some vector represents basically how much of a 0 and how much of a 1 each qubit has. Inner product represents the probability of the two states being measured as the same. This doesn't kind of vibe with what I read in the previous one, so maybe not correct. Can be performed, typically represented by sequences of quantum gates. And then quantum entanglement is a phenomenon in which the state of two or more qubits are linked together. Okay. So the Hilbert space is basically just a space of qubits, but they're entangled with each other, which is why it grows with that order of two, with the order of 2 there. Pure quantum state could be represented by a unit vector. Here's the Ket notation, or the Bra notation. The Ket notation denotes a column vector. Maybe I should have just waited and seen the notations here. And then the Bra notation represents the conjugate transpose of the row vector. So if you do a conjugate of a imaginary number, you're basically flipping. So this is the conjugate of an imaginary number. Let's say you have an imaginary number which has 2 parts here. You have x and y. So x represents the real number, and then y represents the imaginary axis. And obviously the imaginary and the real axes are orthogonal to each other. So when you're taking the conjugate, you're flipping the imaginary part, but keeping the real part the same. So there's a similar kind of thing happening here, where the Bra is the conjugate of the Ket. So this is the same vector, but then with the imaginary part flipped. But in this case, the imaginary part is not, I think it's going to be a phase. So I think in a quantum bit, you have the quantum bit phase. I think the second number represents the phase. Look at all these explanations of quantum computers. That one's shit because it's paywalled. Let's see. Oh my god, all of these pictures suck. Applying a phase gate. Why am I doing this manually? Why don't I just go back to here? What is the phase of a qubit? I think it's the second number. A single qubit can be represented as, those two things. Alpha is the probability of measuring the qubit, and then B is the probability of the qubit in state that, okay. You sum those probabilities, they're going to be 1, so the qubit is always going to be in some state. Complex numbers, we can express them in the polar form. Okay. And then theta alpha and theta beta are the phases. The phase is essentially the angle component of the complex number when represented in the polar form. This angle tells you how the amplitude of a qubit is rotated in the complex plane. Even if 2 qubits have the same probabilities, they can still differ by their phase. Interesting. Phase introduces a new difference between quantum states. It doesn't have any direct analogy in classical bits. Manipulating this phase is a key component in many quantum algorithms. Operations that modify the phase of a qubit are called phase gates, and they can cause interference when the quantum states are combined, right? Makes sense. Qubits have states described by complex numbers where both magnitude and phase determine the qubit's behavior. The phase, in particular, endows quantum algorithms with the power of interference. Okay. What are you guys talking about here? Mixture of experts. Manual mixture of experts. Yeah, that's basically what I'm doing. Okay, so so far we've learned that these qubits exist in our vectors, and they exist in this Hilbert space, and then you are using this fancy notation of kets and bras, and the bras are just the conjugate transposes of the kets, and they're basically a row vector. So a ket is a column vector, and a bra is a row vector. And so it makes sense that the inner product, which would be the dot product, would basically be a number, because you're then going to multiply a row vector by a column vector, and then the outer product is going to produce a matrix. The evolution of a pure quantum state is mathematically described by applying a quantum circuit or a quantum gate. Okay, so you have circuits, you have gates within those circuits, i.e. this. Okay, so here's what a quantum circuit or a quantum gate is. A quantum circuit or a quantum gate is you multiplied this by this vector. So if this ket notation is a column vector, then you can see, and it's a 2 by 1, right? So, or 1 by 2, however you want to say it. Then U is going to be some kind of 2 by 2 such that the output is still a 2 by 1. Right, so this quantum state after evolution or after computation, I guess. I don't know why they use the word evolution. But here you have these quantum gates, and I guess here is a bunch of common quantum gates, such as the Hamard gate and the Pauli operator. So all of these are unitary operators, right? And they're 2 by 2 because the vectors that they're multiplying are 2 by 1. And you can see these seem like kind of basic rotations. So this is like flipping on X, flipping on Y. So Y is the complex plane, right? So maybe kind of like this, right? X is real plane, Y is the imaginary vector or direction, and they're orthogonal to each other. So maybe that's why you have here X, these are real numbers, here Y you have negative. And then I think the Hamard gate, the Hamard gate is important because it puts things in a superposition. That's something that I remember reading, but let's see. Explain the significance of the Hamard gate. Let's put that in there. Put that in there. One of the fundamental 1-qubit gates, so it's a gate that takes in 1 qubit, that kind of matches, okay? Its significance is derived from its ability to generate superposition. Yeah, this is what I remember reading, where basically what is this? Why is it red? This is kind of weird. I've never seen this before, red text. It's probably just because it's going to go back and format it. Let's see. Hamard gate is a fundamental single qubit quantum logic gate. Okay, so it takes in 1 qubit and it's a quantum logic gate. So as we've learned, it's basically this. It takes in 1 qubit and it outputs another qubit. Creates a superposition states from basis states. Applying H to a qubit in state 0 or state 1 puts it in an equal superposition of the two. Okay, so you see how it's basically, rather than being in state 0 or state 1, it's now in a combination of those two. Right, and there's that square root of 2, right? The superposition is the fundamental building block of quantum algorithms. It flips between computational basis states. Applying H twice returns a qubit to its original 0 or 1 state. Interesting. So if you basically had H times this, and then you multiplied this times H, you would get back the original quantum state. It is its own inverse. H squared, I guess that's probably, is identity. Applying it twice undoes the effect. It enables quantum parallelism. Since H creates superpositions, applying it to multiple qubits creates massive parallel states that can be processed simultaneously. Shit. All right, what do we got from here? A Hilbert space is a mathematical space okay, we didn't actually give it the right answer. Here we go. Hamard gate. The Hamard gate is a gate that's used to put a qubit into a superposition of the 0 and the 1 states. This means that after the Hamard gate is applied, the qubit is in a state where it is both 0 and 1 at the same time, right? It's a combination of both of those now. One of the most important gates in quantum computing. Let's see if... Okay, it's still just kept it as a red text. It's kind of a weird... Never seen that. can you format the text above into latex? All right, it's going to take forever. Okay. And their corresponding rotation gates, denoted by RP theta, where the rotation angle theta in 0 to 2 pi, and P in XYZ. Okay, so kind of these looked like rotations across the different axes. So it makes sense that here they're switching to basically polar. I don't exactly know what's going on here, but you're rotating by some angle theta rather than flipping. So here the P, you substitute X, Y, or Z, and this will rotate it by a specific angle theta rather than pure flipping. Multiple qubit quantum gates mainly include in this paper the identity gate, the C0 gate, and the tensor product of single qubit states. Z cross Z, Z cross I, and Z cross to the N. Holy shit, I've never seen that before. Is this done yet? Oh my god. Come on. Come on. Quantum measurement is a way to extract classical information from the quantum state, right? But we did learn that as soon as you measure it, it's going to collapse the distribution, right? That's what we thought here. As soon as you measure it, it'll collapse. Yeah, when a measurement is performed, it collapses to one of the basis states, and the probability of collapsing to a particular basis state is determined by the coefficients of the state vector. Ah, okay. So these alphas and these betas are probabilities. So it's saying this qubit is maybe 50% 0, 50% 1, or maybe it's 80% 0 or 80% 1, right? In the same way that when we were looking at the cat, where is the cat picture? ¿Dónde está cat picture? Okay, maybe we lost the cat picture. But as soon as you measure it, one of these will become 0, and you'll basically lose that information because you won't know what it was anymore. Right? You'll measure it and it'll just be one of these two things, but you'll lose the information that was stored in the probability. So it's like you're storing information in the probability of things. Which is kind of a crazy way to do things. For instance, given a quantum state psi and an observable O, so you have a quantum state psi, which has alpha and beta. You have some observable O. One could design a quantum measurement to obtain the information this. Shit. Okay, so now you have the same quantum state, and they're kind of in a dot product, but there's an O in between that. What does that mean? Does that mean dot product between O and psi, and then the dot product between the complex conjugate of psi and O? Within this work, we focus on the hardware-efficient Pauli measurements, i.e. setting O as the Pauli operators, which are these ones here, X, Y, and Z. In terms of their tensor products, we could choose Z1 equals Z cross I cross N minus 1, X2 equals I cross X cross I cross N minus 2. Okay, I don't know what this is at all. But the fact that they said we could choose means that they decided this. So it's not like... This seems like kind of like an assumption at the very beginning of a proof where they're like, let this equal this. So hopefully they tell us why they chose these, but for now it just seems like they chose these as the operators. Okay. Maybe a little bit of understanding there. You know, we understand what quantum states are. We understand this Braun-Ket notation. We understand what the Hamard gate is, why it's important. We understand how Pauli operators are also different types of operators. The Hamard gate is an operator. We know that if you want to go from classical to quantum and quantum back to classical, you're going to have to collapse the quantum state by measuring it, and you're going to lose information. And with that, let's go to the next section here. Section 1.1.2, text classification. So here, they're going to just introduce text classification is assigning a given text sequence to one of predefined categories. So much like you classify dog and cat images, I guess you could classify text. Here they bring up sentiment analysis, which is one of the most basic forms of text classification. Common adopted approach is to train a model with a set of pre-labeled sequences. This is called supervised learning, where you have a one-to-one correspondence between the input and what the target or the output should be. Pretty much any classification problem is likely going to be solved using a supervised learning approach. When we find a new sequence, the trained model will be able to predict its category based on the experience learned from the training data set. Okay, so that seems pretty standard. Luckily for us, we can understand that part. Daniel Effort, damn, entered while bro was going off on the quantum deep end. Yeah. I mean, and if you guys have good intuition here, I don't know, I'm sure someone in this chat knows more about quantum computers than I do, but feel free to add some context, add some seasoning to my mediocre explanations here. You know, sprinkle a little quantum knowledge on us while we wander around in the quantum realm confused and scared. In a self-attention neural network layer, the input data x of s in r of d. So, okay, much more. This is much more comforting to us. We're talking about real numbers with dimensionality d. You have some input data x, s, and you have a sequence of that input data from 1 to capital S. Okay, so this is much more familiar to us, right? This is back in the normal real world with the big fancy script R and far away from the scary script C, which is the Hilbert space. So we're in the real space here. Are linearly mapped via 3 weight matrices. So these are the 3 weight matrices in a self-attention block. You have your queries, which are d by d. You have your keys, which are d by d. And then you have your values, which are d by d. To the 3 parts, WQXS, WKXS, respectively, and by applying the inner product to the key and query parts. So this is the dot product between the keys and the queries. And then you softmax that and use that to get the values. And that's basically what the self-attention is. And I think here they're just, output is computed as this. They don't have the softmax there, which is a little sketchy. I think this maybe is, no. So y of s, the output, is the weighted combination of the values where the weights are determined by how similar these keys and queries are, right? So the more, if the query and the key agree, right, if those two vectors are pointing in the same direction, the dot product is going to be a high number, right? It's going to basically say these things are in agreement. Therefore, that corresponding part of the value is what I want to pass on to the next layer. When the keys and the queries are not in agreement, right, their dot product or their inner product shows that they basically are unrelated, then you're going to get a big fat 0 here, and that means that that particular part of the value you don't want to pass to the next layer, right? So all the at the end of the day, what a self-attention is really doing is it's basically saying which parts of my keys and my queries are related to each other, and then let me use those to basically modulate and adjust the values of the weights here, which are called the value, which I'm going to pass to the next layer. And then the next layer is another self-attention mechanism, and so on and so on and so on in these transformers. Okay, but I think the way they wrote this like this is because they want, they're going to probably do something here with this self-attention coefficients on their quantum computer. But you can think of basically the self-attention coefficients as the agreement between the keys and the queries. A quantum garnish. So is this through a quantum lens as opposed to classical transformers? No. So this paper is basically a implementation of self-attention with a quantum device, and it's not theoretical. So this is what is called a near. We learned this earlier, but this is called a near something noisy quantum, basically a real quantum computer. So they're saying, hey, we're not going to be using theoretical quantum computers that don't exist yet that are perfect and noiseless. We're going to be using a noisy quantum computer that only has maybe 10 quantum or qubits, right? So here we go. They're using apparently Microsoft Windows PowerPoint here. I feel like I kind of recall this particular font from PowerPoint. Sketch of a quantum self-attention layer. On quantum devices, the classical inputs, so your inputs are classical in that they are actual real numbers, right, like this, real numbers of some dimensionality d, are used as the rotation angles of quantum ansatz. So ansatz is the German word for initial condition, right? Quantum ansatses. Ansatz is a circuit with a predetermined geometry, so geometry basically connectivity, and gates that express a time evolution unitary operator. Okay, so unitary operator is, we've learned, is basically just one of these matrices here that you can multiply by a quantum state. One of the most well-known ansatses is a hardware-efficient ansatz, which minimizes hardware noise using native gates and connective. Okay, so it's basically just a quantum circuit. And those are the purple dash boxes, so this box here. So this box here is a quantum ansatz, this box here is a quantum ansatz, this box here is a quantum ansatz, and I think the L refers to the layer. So here we have layer L minus 1, and here you have layer L. So you're going to have many of these layers. So here the input to layer L is the output of layer L minus 1. Maybe this here is a residual connection. So you see here how the output of the previous layer is going and getting fed into the next layer. So that seems like a residual connection to me. Here you have Y1, Y2, Y3, possibly a sequence of text, a sequence of tokens. Each of those tokens is going into its own little quantum ansatz. We see here how the state is 0, 0. This is a quantum state here, quantum bit. There's, I guess, 3 bits per quantum ansatz. And then that output is producing this psi1, psi2, psi3, which I guess is probably a more complicated state, possibly a superposition, right? I bet you one of these little things in here is the Hamard gate, which puts it in a superposition. To encode them into their corresponding quantum states. Okay, so you are taking these tokens and encoding them into a quantum state, and the quantum state is just a superposition of 0 and 1. For each state, there are 3 different classes of ansatz, red dash boxes. Okay, so you have 3 different red dash boxes for each quantum state here. Where the top 2 classes denote the query and the key, and the bottom one denotes the value. Okay, so here is your query, your key, and your value. So you guess that makes sense here. You have ZQ, ZK, ZQ, ZK. So you have queries, keys, and values. In a classic self-attention mechanism in a transformer, those are shared. So you're using the same query, key, and value matrices for all of the parts of the input, which is why you can parallelize it and it's nice and fast. I suspect they probably do something similar here, so I bet you this ZQ1 might be the same as this ZQ2. It kind of looks like it's the same, so you see here how it's the same color. It's like the same weird, like, beige color, then this same weird noisy color, and then the same weird brown color. That's repeated, so that's making me think that these ansatzes, the red dash boxes here, are shared amongst all the different inputs. On a classical computer, the measurement outputs of the query key are computed through a Gaussian function to obtain the quantum self-attention coefficients. So this is a hybrid approach. Is that what they're saying? We calculate classically weighted sums of the measurement outputs of the value part and add them to the outputs. Classically weighted sums of the measurement outputs of the value part. Okay, so that's effectively this. You have a sum, right, over all inputs. Inputs here are xj, outputs are y, but here in this diagram, it's a little bit more confusing because the outputs are yl minus 1, or the inputs are yl minus 1, versus here the outputs are yl. So just imagine this here says yl minus 1, and this here says yl, but you're summing over the weighted by the query and the key dot product of the values. Okay. and add the inputs to get the outputs, where the weights are then the normalized coefficient. Alpha Sj, which is what we had here. Okay. So here they're adding together the output of the keys times the queries, I guess. So here you have the keys, the keys, the keys. They're getting multiplied by the queries. That's how you get this alpha. So here's your dot product. Then once you have those three alphas, you use those to multiply the actual values, which are coming out of here, right? So here's your value matrix, XYZ, your values, XYZ, your value, XYZ. You're using the value, you're multiplying it by the output of the dot product between the keys and the queries, and then you add all of that together, and you get the output, which you would then feed into your next layer. This is kind of a confusing diagram here. You see how there's a plus sign, so you're adding them this way, and the dot products are going this way. And that's basically that. Okay, we kind of have an idea. It seems like the only part, so it seems like all of this is classical, right? So actually adding together all the weights, adding together the values which are weighted by the dot product or inner product between the keys and the queries. This is classical, which is what they're telling you here, on a classical computer. So all this part here is being done on a classical computer. The quantum part is just this here. So really the only part that's quantum is getting the queries and the keys from the input states. Right, so it's really, you just have these ansatses here, these quantum circuits here. Okay. We will introduce the QSAN in detail. This is the quantum self-attention neural network, which mainly consists of quantum self-attention layer, a loss function, analytical gradients, and analysis. Okay, so up until now, we've just been looking at the kind of the forward step of like, okay, you have inputs, you feed them through this self-attention, and it produces some output. But eventually, you're going to want to train this thing, right? You're going to want, there's parameters in here, and you're going to want to optimize the values of those parameters with respect to some training data. So in order to do that, you're going to have to start thinking about what's the loss function, and then how can I actually get the gradients for this, right? Can I chain rule? Can I chain rule through a quantum ansats? I don't know. Let's see. Quantum self-attention layer. In the classic self-attention mechanism, there are mainly three component vectors, i.e. the queries, keys, and values, where the queries and keys are computed as weights assigned to the corresponding values to obtain final outputs. Inspired by this mechanism in QSAN, we designed the quantum analog of these components. Okay, so it's in this paper, it's not like they came to the idea of self-attention as being a very good fit for quantum circuits. They kind of went the opposite way, right? They came from the perspective of like, hey, it seems like self-attention works very well in classical computers. If we try to implement it in quantum computers, will it also work well, right? So they kind of are going backwards, going from like, hey, this works well in classical, let's try it in quantum, rather than, hey, we derived some nonsense over here in quantum theory world, and then now let's move forwards from that. So you have your classical input data. This is a little annoying. Right here, your input data is X, and here the input data is YSL minus 1, meaning the output of the previous layer. So a little bit annoying. I feel like they should have just kept that notation at the beginning there. We first use representing the Lth layer, so the Lth quantum self-attention layer. We first use a quantum ansats U encode. So actually we're seeing a little bit of convergence here on the terminology. So a quantum ansats U encode is the same thing as a unitary operator, which is basically just a matrix. So the Hamard gate is a U. These poly operators X, Y, and Z are also U's. And now we're learning that these little quantum ansatses, these little quantum circuits, are also U's. So everything is a U. So here specifically, they're saying, okay, so we have some U encoder, and that U encoder, first we have our qubit, our state here, or quantum state, which is this vector here. that quantum state is getting multiplied by the Hamard here. So this is the Hamard based on what we've learned. It's basically, where is it? No, that one sucked. The Hamard gate, H fundamental, creates a superposition of states from basis states. Okay, so we're basically taking our basis state here, which is 0 to the n. You have all of them are in basis state 0, and there's n qubits. Then you're Hamard gating them to put them in a superposition of both 0 and 1. And then you want to figure out some operation, U encoder, that is based on the output or what you want as input. And that's going to produce the actual quantum state here, psi s. And you have S total, where S is basically the length of the sequence. Okay, so what are we going to do with this U encode? Where H denotes the Hamard gate, S denotes the number of input vectors in the data sample. Okay, so the length of the sequence. When we use another 3 quantum ansatses, U, Q, UK, UV, okay, so our keys, queries, and values, we're not going to represent them as matrices, we're going to represent them as these quantum ansatses or U, but we know that a U is basically just a matrix with parameters theta Q, theta K, and theta V, okay, to represent the key, query, and value parts. Concretely, for each input state, so you have your input quantum state psi s here, of which you're going to have S total of those. We denote by ZQS and ZKS the poly Z1 measurement outputs of the query and key parts. Okay, I don't know what the poly Z1 measurement outputs. So we know that the poly operators, there's an X, there's a Y, and there's a Z. So the X and Y, I think, are analogous to the X and Y real and imaginary axes here, and then I guess Z is basically the right-hand rule orthogonal to both of those. So Z1, what is Z1? Maybe if we actually just look at this equation, it'll make more sense. So we have our original quantum state, psi of S. We're multiplying that by our U query, which is parameterized by theta queries. Then we're multiplying that by this Z1. Same thing is happening here except for the keys. Then we're multiplying it by the complex conjugate of our U keys and U queries. And then we're multiplying it by the complex conjugate of the original quantum state. So it's kind of this weird thing that we saw up here with the O, where they're taking the quantum state and then multiplying it by this observable O, and then multiplying the complex conjugate by that. So it's kind of this weird kind of thing here where they basically put something in between the bra and the ket. And now they're basically doing the same thing, except what's in between the bra and the ket is this U query, the Z, and then the U query conjugate of that. The measurement outputs of the value part are represented by a d-dimensional vector. Okay, so we have a d-dimensional vector. The dimension d comes from the actual classical input data, right? So your classical input data has some dimension d, which is separate from the sequence length. So it's a sequence of tokens of each token is of dimension d. So you have some d-dimensional vector, which is the observation or output. Holy shit, what is going on here? PJS equals psi s UV transpose PJ UV parameterized by theta v, and then ket psi s. PJ I, X, Y, and Z denoted poly-observable. So I'm starting to think that the whole point of these poly observable things here is that basically this is how you actually do the measurement. So these p's, which are basically one of these, either the identity, the x, or the y, or the z, are basically saying, once you have this in there, it means you're measuring it. What is Z1 again? I think Z1 is this. They define it here. Z1 is Z times identity of cross n-1. I don't know what this notation is. Single qubit gates. Let's search for this. Let's do control copy. See, put it in here. Nope. Can I copy this? Help me understand this notation. Let's go to 2 here. Let's go to 3 here. All right. Here's the information. Single qubit gates, properties that act on a single qubit. Okay, so that makes sense. It's just a 2 by 2 because it operates on a single qubit. Common single qubit gates include the X, Y, and Z in the Hamard gate. Okay, we kind of knew that. The tensor product is we want to describe the operation gates on multi-qubit systems. We use the tensor product to combine gates. The tensor product allows us to describe the joint state or joint operation on multiple qubits. Okay, so whenever you see this cross product, here it's actually called the tensor product, you're basically saying, I want this Z gate, but the Z gate applied to all qubits, not just one qubit, because this Z is just a single qubit gate, but now you want to apply it over a bunch of inputs or a bunch of tokens in your sentence. Represents the tensor product of 2 Z gates acting on 2 qubits. As Z gate acts on the first qubit, another Z gate acts on the second qubit simultaneously. Z cross I here is a Z gate acts on the first qubit while the second qubit undergoes an identity operation, meaning it remains unchanged. And then Z cross N here suggests that Z gate is acting on each N qubits. For each instance, if N equals 3, it means Z acts on the first qubit, Z acts on the second qubit, and Z acts on the third qubit. Okay, that kind of makes sense. Let's see if this makes sense for Claude as well. Refers to applying single qubit quantum gates to specific qubits within a multi-qubit quantum system. Okay, so the same kind of idea of like the Z is really just a single qubit gate, and now you're just trying to apply it to multiple qubits. Z refers to the poly-Z quantum gate, which flips a qubit state from 0 to 1 and vice versa. Okay, so that's really what the Z gate is doing. Cross signifies the tensor product, indicates that the gates act independently on separate qubits. This is kind of what, this makes sense as well. And the single qubit identity gate. Z cross Z applies poly-Z gate to the first qubit and poly-Z gate to the second qubit in parallel. Z applies to the first and then does nothing to the second, and then poly-Z to the first and identity qubits 2 through N. So you see, this is actually different than what we got here. I kind of think the ChatGPT one is probably a little bit more, this seems more correct. Let's see if Bard. Single qubit gates represents poly-Z gate that is applied to 2 different qubits, and then the Z applied to the nth qubit in a quantum register. Okay. Does that kind of make sense? So here you have the identity of n-1, so I guess this means identity operation applied to all qubits up until the 1 that you're interested in. Here n-2, so 2 before that, and then you apply the x and then the I. So these are basically like operations applied kind of sequentially here. So you have the identity for all of the ones up until n minus 2, and then you apply the z, and then you apply the z again. Okay. And now if we go back here, ZQ is equal to this. I'm still definitely a little bit confused here. Combining the classical outputs of the nth QSAL are computed as follows. Okay, so really, actually, here, if we just see the quantum, or the classical version of this, right? You have your weights, or your values, are getting multiplied by the dot product between the keys and the queries here, and you're summing over all of those. So the same thing is happening here. You're taking the dot product between your keys and your queries, and you're summing over all of those. And then here you have the residual connection. So that must mean that this here is basically the values, or the dot product, or no, the values. So the values, the value matrix is this, right? You're summing over all, j equals 1 to s, O of j, O of s, so there's s total here. And the dimensionality of that is d. And then each element of that is the dot product. I don't know, guys. I don't know. I don't know about this. We're flipping the value of the last qubit. So if the z is a flip, where did they... I think there was a nice definition here somewhere. Where was the nice definition? Yeah, flips the quantum qubit state from 0 to 1. So if z is a flip, then here you're just flipping what's coming out of here. I don't know why you need to flip it like this. It's not looking good. Let's just calm down and maybe keep going, and then maybe we'll come back to this, or maybe we'll get a little bit more understanding later. Alpha tilde Sj denotes the normalized quantum self-attention coefficient. So normalized self-attention coefficient makes sense. The quantum, I guess, refers to the fact that here they just plugged in the quantum states between the Sj and the jth input vectors. S and the jth input vectors. So this is the self-attention, the two dimensions there. You have S on one side and then J on the other side. Calculated by the corresponding key and query parts. ASJ, the sum, this is the normalization here. So you're summing over all. J from 1 to S. There's a little bit of annoying notation here, but here they're basically, you have some sequence, and in self-attention, right, you have to multiply the dot product between everything in the sequence and everything else in the sequence, right? So you have two indices, one denoting the x and one denoting the y-axis. So here the indices, they're using J and S, here they're using M, so they're kind of switching the variable that they use to denote the index of the where you are in the sequence, but that's largely what's going on here. And then here you just have ZQ and ZK, which are the Q and K operators. I think what confuses me about this is that, like, won't this times whatever the fuck this is produce a number? I guess not. If this is a column vector. Let's make sure we're correct there. So let's go up here. Holy shit, where is it? Right here. If ket is a column vector, and these big capital letters are basically 2x2s, then what is going on here? You have, nope, too far. We have a column vector, a 2x2, another 2x2, another 2x2, and then a row vector. So shouldn't this just be a number? Adopt a residual scheme when computing the output, which is analogous to 36. Attention is all you need. Oh, I think what they're talking about here is that the residual scheme is this part here. It's the residual part, right? The fact that you're taking the output of the previous layer and then kind of feeding it and piping it into the next layer, right? That's analogous to the former all you need. It's this part here, right? So here you have this residual connection that's going around the attention mechanism. So that's basically this here, which is the residual. And they reference the attention is all you need. So there you go. I don't think I answered your question, Luke, but I'm just going to keep going. I'm sorry. Gaussian projected quantum self-attention. Okay, so we kind of now have an idea what quantum self-attention is, and now what is Gaussian projected quantum self-attention? When designing a quantum version of self-attention, use a natural and direct extension of the inner product self-attention to consider is alpha Sj. So the magnitude of this squared. Okay? However, due to the unitary nature of quantum circuits, can be regarded as rotating psi by an angle. Okay, maybe actually here we have learned a little bit more where this is rotating by an angle. Does that help us understand anything here? Not really, because here you have Q and Q and K, and here it's Q and K, which makes it difficult for psi s to simultaneously correlate those psi j that are far away. In a word, this direct extension is not suitable or reasonable for working on the quantum self-attention. Instead, the particular quantum self-attention proposed, which we call Gaussian projected quantum self-attention, this one here, I guess this is the Gaussian where they're projecting it, could overcome the above drawback. The state in Gaussian projected self-attention, UQ psi s and UK psi j in a large quantum Hilbert space are projected to the classic representation ZQS and ZKJ in a one-dimensional classical space via quantum measurements. Okay, so this is a measurement. So you're measuring... okay, this makes so much more sense. All right. So this is a row vector, or this is a column vector, and this is a row vector. So if you're taking a column vector and multiplying it by a bunch of 2x2 matrices, and then ultimately multiplying it by a row vector, you're going to get a single number. And that's where I was confused. I was like, shouldn't this be more than just a single number? But no, it actually makes sense because it's a measurement. The measurement output collapses the quantum state into a single value, right? When you haven't measured, the cat is both alive and dead, some combination of the alive and dead. But as soon as you measure it, now it's either alive or dead. So that makes sense that this is just a single number, right? So this ZQS, what you're doing there is you're collapsing this 2x1 into a one-dimensional classical space where it can only be one thing. Yeah, I think that makes sense for me. John Egan, Z performs a phase flip on the quantum state. In one state, it multiplies by -1, leaves it unchanged if in zero state. Thank you, John. But yeah, I think this projected to classical representations in one-dimensional classical space. That sentence right there is what made it make sense to me there. Via quantum measurement, and a Gaussian function is applied to these classical representations. As UQ and UK are separated, it's pretty easy to correlate psi s and psi j, making GPQSA more suitable to serve as quantum self-attention. We utilize a Gaussian function. They keep talking about this Gaussian function here, like, let's see. Like Gaussian is another one of those terms that has like a bajillion different definitions depending on like where you're using it. So like, let's see exactly what version of a Gaussian function they're talking about here. Call a function k. Is this it? Some function k where k is from... Oh my god, this paper is even worse. The space of kernel sections. Dude, what the fuck? All right. Do we want to refresh? I don't want to refresh because I don't want to lose that context. You know, like when you're asking GPT like this and any of these AIs, like having a little bit of a conversation beforehand is actually kind of useful because it provides it a little context. Let's see this. Infinite dimensional feature space and well-studied classical machine learning. Why don't we just copy this entire paragraph here? What is the Gaussian function in this paragraph? Control 2, tab, Control paste, enter, Control 3, paste, enter, Control 1, Control 2. The Gaussian function being referred to this is the exponent of, which is exactly what we saw there. Yeah, here it is. Okay. The classical representations obtained by measuring the quantum states. The distance between two classical representations, the standard deviation parameter of the Gaussian function. There is no standard deviation there. See that? That's not there. The quantum states are projected through measurement. The Gaussian function is applied rather than the quantum states directly. Using the Gaussian creates an infinite dimensional feature space to correlate the quantum states. I don't really understand this, why that makes sense yet. Let me see. Let me see if GPT has a better reason. Gaussian function is a well-known mathematical function with a bell-shaped curve. Okay, so Gaussian function is just a fancy way of saying Gaussian. This entire time, it was literally just that. This is the Gaussian function. And then this is the normalized Gaussian. So they're literally just putting the difference between these two things into a Gaussian. Applied to the classical, likely to provide some form of similarity or distance metric in the transform space. Infinite dimensional feature space. What does it mean by infinite dimensional feature space? The Gaussian is not infinite dimensional. I guess it's continuous. It has an infinite input space and output space. You can put in any number and it'll give you any other number, but you can define a Gaussian with a mean and a variance. So it's not infinite. My eyes are bleeding. I think John Egan has some help for us. John Egan's coming in to save us here. The kernel trick allows nonlinearly separable to become linearly separable. Kernel trick is the earworm. What is an earworm? The Gaussian function properties, okay. Particular kernel methods like Gaussian radial basis RBF kernels and support vector machines. How the Gaussian is applied suggests that the Gaussian function helps overcome some limitations. I'm still confused, guys. Numerical experiments also verify our choice. We also note that other choices of building the quantum self-attention are also worthy of future study. Okay, so this is basically it's kind of an arbitrary choice, but they're doing it. The ansats used in QSAN. So the ansats, which means one of these little bubbles here, I guess it's probably this first bubble. The first two columns denote the Rx, Ry rotations on a single qubit subspace, followed by the repeated C0 gates. Okay, so here you're rotating on X by some theta, you're rotating on Y by some theta, rotating on X and then Y, X and then Y, X and then Y, so all of these are the same rotation operations here. You have C0, so you have some sort of like weird addition here. Repeated D times to enhance the expressive power of the ansats. So why do you repeatedly apply these rotations? Explain this sentence. Projecting the states, Gaussian function is a bell-shaped curve centered on the origin. Well-studied function, blah, blah, blah. Centered at the origin, so it will amplify the correlation that are close to the origin and suppress the correlations between the states that are far away from the origin. Gaussian transformed are then used as inputs. Okay, let's go back to the question we were actually trying to answer here. Oh no, dude, we've like permanently fucked up ChatGPT. Like, oh no, maybe not. Look at that. It's actually giving us little matrices here. Quantum circuit, which is an ansats, which we found out earlier. The ansats is a term bought or applies to a guess or an assumption. So you have Rx and Ry, which are rotation gates or rotation matrices. So those kind of make sense. You have a rotation matrix in X, which is parameterized by some rotation angle theta. The controlled NOT gate, abbreviated as C0, is a 2-qubit gate. Okay, so pretty much everything we've dealt with has always been a 1-qubit gate, right? The Z is a 1-qubit gate, the Hamard operator is a 1-qubit gate, but now here you have a 2-qubit gate. One qubit acts as the control and the other as the target. If the control qubit is in 1, then the target qubit is flipped. If the control is in 0, then the target remains unchanged. Okay, so this is kind of similar to your standard classical computing gates, your like AND gates, OR gates, NAND gates. There's a bunch of these gates, but basically what they're doing is like, here, classical computing gates. Here you go. So these are your standard little logic gates that you probably learned in school and that I already forgot about, but open image in new tab. NOT gate. So if you have 0 and 1, or these are more interesting, the ones that have 2. So these are 1 input, but these are the ones that we're interested in, 2 inputs. So you have an input A and an input B, and it produces some output Y. And the output Y is going to depend on the input A and the input B. So for example, this AND gate, 0, 0 makes 0, 0, 1 makes 0, 1, 0 makes 0, 1, 1 makes 1. So that's the basic idea of these, and I guess there's a quantum version of one of these kind of things, which is called a controlled NOT gate. Okay. The sentence suggests a sequence of these gates applied to pairs which can create and manipulate entanglements. Okay. So I think that's the whole point of this gate, is to entangle the qubits, right? So you have, I guess, 4 separate qubit states coming in here, right? And then you're rotating them, but then adding these C0 gates, which I think are these, such that they become entangled with each other. Okay. Sequence sketch of QSAN, where a sequence of classical vectors XS first goes through L quantum self-attention layers to obtain the corresponding sequence of feature vectors YSL. L, I guess, is the final layer, capital L. Then through the average operation, and finally through the fully connected layer for the binary prediction task. So it's a classification task. Binary prediction basically just means binary classification, which means it's going to predict category 0 or category 1. There's 2 classes or categories in this classification task. And here is just a simple little head. So basically they're almost using this as a kind of like there's a backbone and a head in a lot of neural nets. And the head is task specific. And here they have a task specific classical computing head for binary classification. And then the backbone, or sometimes called the encoder, but not so often anymore because that term is kind of overloaded. But the backbone is the actual quantum self-attention neural network, which has multiple quantum self-attention layers. So you see here quantum self-attention layer 1 all the way to layer L. The raw input is called X, and then the output of that will be Y, L minus 1, L minus 2, and so on until you finally get to YL. The length of the sequence is this. Here they just show 3, but eventually you would have S of these, so X1 to XS. This makes sense. This kind of doesn't make sense. I see why, or we kind of understand what's going on, right, where they're putting it through these C0 gates because they want to get entanglement. But maybe this. The structure is repeated D times. Repeating circuit structures is a common technique in variational quantum algorithms to increase the expressiveness or capability of the ansats. It allows the quantum system to explore a more diverse set of states which can be useful in optimization tasks. Applies a series of C0 gates, blah, blah, blah. Okay. Entangle the qubits by linking them through conditional operations. So you link them through these C0s. Another set of rotations are applied. Okay, so here are your rotations applied after the C0s. Ansats consists of single qubit rotations, C0 entangling gates, more rotations, and then repeated steps 1 through 3. So it's kind of interesting how, like, in deep learning, right, you have many, many layers, and you can think of them as entangling each other, right? So like every neuron in a neural network, right? Every neuron in a neural network in a classical sense has some dependence on the previous, right? You have full connectivity here, which means that this neuron is, the output of this is fed into every single neuron in the next layer. So you could think of it, if you kind of blur your eyes enough, as this, there's some, as the way that Claude put it, it's entangling the qubits by linking them through conditional. So the output of this neuron is conditional on the output of all these previous neurons. So in a sense, it's kind of entangled with these neurons, except here in an actual quantum computer, we're like legit entangling them. Right, so here you have actual quantum entanglement, not just it's conditional on the output of the previous thing. But the actual ordering of these C0 gates here, I have no idea what the fuck. Like, why these, and that? That seems really weird. John Egan for the support here. The kernel function maps inputs. Earworm is a song or a tune that gets caught in your head. Okay. I think that entanglement can be thought of as improving processing speed. Okay, so somehow this entanglement makes things faster? Is that what you're saying? So we notice here how the if this is the C0 gate, right, the C0 gate looks different for these different ansatses. You have the same ansats here, right, where you have this input is then C0'd with this input, but you have a different C0 kind of, or different ansats, different wiring in this quantum circuit here. So that's something that they haven't really explained. During the preparation, as well as after submitting our work to a peer-reviewed conference, we became aware that also made initial attempts to employ the attention mechanism. Uh-oh. So they had to add this little section because other people were trying to do the same thing. So it kind of makes sense, right? September 2021, transformers starting to become even more popular, so they probably weren't the first quantum researchers to be like, hey, we should probably try to implement the self-attention in quantum computers. So it seems like they got beat to the chase by some other people, and they're trying to, let's see, authors mention a possible quantum extension where a straightforward inner product and self-attention is adopted. As discussed, the inner product self-attention may not be reasonable for dealing with quantum data. In this work, we present GPQSA as more suitable for the quantum version of self-attention and show the validity of our method. Okay, so basically somebody else tried to do what they tried to do, and they said, our thing is different enough that we're still going to publish this paper, and we're going to actually show that our stuff is better. But note here that it's the word validity of our method, not superiority of our method, because these aren't even... I don't even think there's benchmarks for these kind of things. You know, there isn't like a benchmark for quantum text classification, so they can't even compare to the authors of this work. So the best they can say is that, hey, our method works. So we don't care if your method works, but our method works. Ansatz selection. Okay, so maybe we do get a little explanation of how the fuck they get these C-naughts and decide where to put the C-naughts. We employ multiple ansatses for the various components: data encoding, query, key, and value. Okay. Hence, we give a brief review about it here. In general, an ansatz, aka a parameterized quantum circuit, has the form U theta, pi j, uj, theta j, vj. Okay, so you have a multiplication, cumulative product, right? That's what this pi is. You're multiplying a bunch of these UJs, which are parameterized by theta, together. That makes sense. So VJ denotes a fixed operator such as the identity, C naught, and so on. Okay, so VJ is actually C naught. So you have C naught multiplied by a bunch of UJs, which is actually kind of what we were seeing up here, right? This actually looks a lot like that. You have Z, and then you have these U's. Okay. Uj theta j equals exponent of negative theta j pj over 2. Okay, I don't know what that's supposed to mean. And then pj is the Pauli operator. Okay, so it kind of seems like with these Pauli operators, the Pauli operators seem like the kind of base, like they're kind of like the basis vectors. You know, they're kind of just like the basic form of an operator. And then anytime you make a new operator, you're basically saying, okay, it's like the Pauli operator, except we're going to add a little extra variable here, theta j, and then that's the variable that we're going to change. That's the variable that we're going to learn, and over time, that variable will become better and better and better at doing, at making this circuit do what we want it to do, right? So if you're doing machine learning, you have to have some kind of parameter that you're optimizing. So in this case, they're saying, okay, well, we're just going to take these Pauli operators, we're going to put them in this form here, and we're going to have these little variables, theta j, and then we're going to learn the best thetas for our text classification. Okay. Due to numerous choices of the form of VJ, various kinds of ansatses can be used. Okay, so you don't necessarily need to use C naughts, right? You could technically use any gate, any one of these gates, or the quantum equivalent of these gates, that all, because basically all you want them to do is you want them to entangle the two states. In this paper, we use the strongly entangled ansatz, as shown in Figure 2 in QSAN. This circuit has n d+2 parameters for a total of n qubits and d repeated layers. Okay, since these U operations each have one parameter, if you have n qubits and then d of these layers, so you see how they have a times d here, so there's d of these blocks repeated over and over again, you're going to have this theta here times d. So that's how many parameters total you're going to have. So they don't really have that many qubits, so they don't really have that many parameters, right? Like if they only have 100 qubits and they have, I don't know how many, 10 layers, then you're only going to have 100 times 12. These are tiny amounts of parameters, right? It's not even close to like the 500 billion parameters in Palm, which is why you're doing basic binary text classification. But it kind of gives you an idea of where we are at with quantum machine learning, where we're still just making these tiny little quantum neural nets with a tiny amount of parameters and training them on tiny data sets and getting tiny results and making tiny conclusions. All right. So now that we've not understood any of that, let's look at the loss function. Seems crazy to me that quantum computers use different explicit logic gates. You can make any logic gate out of a bunch of NANDs. So you're saying you can pretty much create anything out of a NAND. Yeah. There's probably other reasons why they chose the C0. I bet you the C0 is like easier to make in the actual world or something like that. What is a quantum C0 gate? Like, can I just buy one of these? The C0 is a common and useful gate in quantum circuits. It takes 2 qubits, controls the qubit, and outputs 2 qubits. Why is it popular, though? You know what I'm saying? Like, is there some mechanical reason why it's popular? Is it, like, easy to implement? The fuck is this? Quantum Inspire? Can I, like, run this? Open an editor? Oh, shit, look at this. You can make little quantum circuits. Execute the Hamard gate on qubit 0. So we start with a state of 0. So qubits 2. Let's have 2 qubits. You have a Hamard gate on qubit 0, and then you entangle both qubits in 1 using the C0 gate. And then I wonder if you could do something like this. 4i in 5. No, this is not Python. It's like, what the fuck are you talking about? But this is kind of cool. Accept cookies. Hamard gate. Poly Z gate. Dude, this is what we should have been looking at this entire fucking time. Look at this. Initialize a 5 qubit state. The poly X gate is a single qubit rotation through pi radians around the x-axis. The poly Y gate is a single qubit rotation through pi radians around the y-axis. The poly Z gate is a single qubit rotation through pi radians around the z-axis. Identity gate, RX gate, RY gate, S dagger gate. Sounds cool. C0 gate. So here's all these different gates. It's pretty badass. And then what is the measure operation? Here's the measure. The measure instruction. So what if we measure Q of 0? Oh, look at that. And we added a little measurement. Oh, shit. Look at that. Okay, so this little almost looks like a speed dial means a measure gate. So actually now, if we go back here, now we know what these are. So actually, if you looked at these things, there was these little, you see that? See that little shit right there? That little, it looks like a speed dial. That's the measure gate. So we know what this is now. We've figured out what these little things are. So, and that makes sense, right? It's once you're done doing all your quantum stuff, you measure it, right? You measure the actual qubit, which means you collapse the state. It is no longer in a superposition. It's now a specific thing, and now you do all your classical computing. Oh, pretty good. Okay, where were we at? We were here, loss function. Consider a data set this. Okay, so you have pretty standard data set. You have some amounts of inputs, of which there are, I guess, n of them. There are a total n of s sequences of length s. each has S of M words with a label Y, 0, or 1. So this is the binary classification problem, right? So every sequence has either a 0 or a 1. We assume each word is embedded as a d-dimensional vector. So each our thing is tokenized into these d-dimensional tokens. The whole procedure of QSAN is depicted in Figure 3, which mainly consists of LQ cells to extract hidden features and one fully connected layer to complete the binary prediction task. So this is the one fully connected layer. This is a classical computing head, right? So this is like just a standard little neural network head that basically has two outputs here. You're sigmoiding it to turn your logits into probabilities so that you can perform this binary classification. And then you have your L layers of quantum self-attention. And they're just using a mean squared error, right? So here you go. You're taking the 0 that is true, and then the prediction. So this is the actual ground truth. This is your prediction. You're summing over all of the sequences in your data set, and that is your loss. And your loss is a function of all these things here. Your loss is a function of all parameters of the ansats, the weights and biases of the final fully connected layer, right? These two here. And then D, which is your data set itself. Okay, so I mean, this makes sense, but how are you going to, you're going to be, I can see how you can make these W1s and these like this is pretty standard. You can back propagate to here. That makes sense to me. But how do you back propagate into this quantum shit? That's what I want to know, right? Your loss function is here. You're going to be using the ground truth, and you're going to be able to push gradients. You're going to be able to update these W's and this B here of your little final layer, but how are you going to push those gradients all the way back into these quantum layers so that you can adjust these thetas, right? These parameters that are modifying the polygates. All right, denoting sigmoid activation function, reg term being the regularization term to avoid overfitting. Okay, so they have additional regularization. Your loss function is actually a two-part loss function. Combining equations 3 to 7, we know that the output of each quantum self-attention layer is dependent on all its inputs. Okay, so you have the parameters of the queries, the parameters of the keys, and the parameters of the values for each layer L. You have the output of the previous layer, and then you have the output of this layer. So the output of this layer is a function of the output of the okay, that makes sense. Here you're actually doing, this is the keys, or not the keys, this is the output of the dot product of the keys and the queries, right? What normally called the values. So this is the weights that you're multiplying by your values in order to get how much of your values matter. Jesus Christ. I hate the fact that the word values is used. All right, I'm getting confused. I need more yerba mate here. Okay, but I mean, so far they're not really doing anything here. They're not telling us how they're going to back propagate into these quantum things. 1 to less than S, less than SM. Here the regularization term is defined as this. Okay, so they're regularizing W. So regularization terms, you add them to loss functions in order to potentially reduce the magnitude of certain things. Here it sounds like they're, what is this W? W and B, or not, the weights and the biases. So they're penalizing the weights of the final head. So you see here, if the weights of the final head get too big in magnitude, then this term is going to start going up, which means your loss will go up. So if you put this in your loss function, it's going to make sure that the weights in that final layer aren't huge. Same thing here, I guess. You're regularizing, isn't that the input? Where Lambda and gamma are two regularization coefficients, aka hyperparameters that you're just going to pick. So the lambda and the gamma are basically going to determine how much more important your regularization is or less important than your actual loss function. You want most of the loss and most of the gradients to be a result of your loss function, not necessarily these regularization terms, which is why this gamma and this lambda are probably quite small. With the loss function, we can optimize its parameters by stochastic gradient descent. The analytical gradient analysis can be found in the appendix. They're burying the lead. I think this is the hardest part. With the above, we could train our QSAN to get the optimal or suboptimal parameters. See algorithm 1 for training details. Okay, so here's the algorithm. We remark that if the loss converges during training or the maximum number of iterations, the optimization is stops. Okay, so that's pretty standard training procedure there. Training data set. You have some number of epochs, which is how many times you're going to go through your training data set, and a number of quantum self-attention layers L. Your output is the final ansatz parameters. This is what you want, right? You want the parameters of your quantum self-attention layers, and then the parameters of the final little head that actually outputs the prediction. You initialize them. It'd be good to know what they're initialized as. You know, like, are they... There is fancy initialization schemes for neural networks. There's like Xavier initialization. You can initialize all to zeros. Here they're initializing the weights of this final little head to 0, a normal distribution with 0, and then 0.01. So they're a little noisy, but what did they initialize these ansatz parameters to, right? That I have no idea what the fuck they would initialize that to. Then you go through your data set in episodes, of which there are an epoch number of them, and then you go through each of the sequences. You apply the U encoder ansatz to get the corresponding quantum state. So you have to start with a classical input, and you have to turn it into a quantum state, right? And in order to do that, you're using this encoder ansatz. You apply the query and the key ansatses to the quantum state to measure the poly Z expectation. So you apply your query and your key, and then get the collapse it to get this actual final number, which is your measurement. And then that final number gives you your self-attention coefficients, which you're going to multiply by your values. Your values are going to come from applying the UV ansatz to measure a series of poly expectations to get O of S. O of S is your values, and then compute the output of the Lth QSAL. Repeat 4 to 6 L times, so there's 6 layers total in their quantum self-attention neural network. It's only 6 layers deep, so it's really not that deep, to get the output of the Lth QSAL. Average YSL and through a fully connected layer to obtain the predicted value. This is just the head. Calculate the mean squared error and update the parameters through optimization. This is the hard part. You got to tell me how you do that. This is the part I have no idea how you're doing it. QSAL first encodes words into a large quantum Hilbert space as the feature space, then projects them back to a low-dimensional classical feature space by quantum measurement. That's a pretty good sentence. How many quantum computers are there? Could we get access to one, or is there like 3 in the world and you have to be in Oxford or something to get a shot? You can simulate them. Penny Lane. So this is a website that someone on the Discord shared that's actually really pretty good. Like, I was going through some of these, but basically there's like this entire Python library called Penny Lane, which import as QML, and you can create little circuits, right? So you can simulate devices of 2 qubits, 3 qubits, 4 qubits, whatever you want, and then basically write code and then see what it would look like. Now, if you actually go to their GitHub, right, one thing I noticed here is that much like when you write PyTorch and TensorFlow, you're compiling it so that it runs on a CUDA device, or you're compiling it so that it runs on an AMD GPU, right? You're compiling this code into the actual hardware that it runs. So this penny lane GitHub is the same thing, right? It's basically like you write the actual circuit and the code that you want to run, but then it'll run the same circuit on different quantum backends. So the same idea of like you have a CUDA backend or an AMD backend or whatever you want, there's a similar notion of a quantum backend. And here you have Amazon Bracket, IBM Q, Google Circ. So I think all of these are quantum computers, right? Like if we do Amazon Bracket, quantum computing research. So you can basically you can rent out quantum computers, 1 free hour of simulation time. I guess this is a simulation. One of these has to be real. I think Google Circ is probably real. No. Hardware, here we go. Our goal is to build, but can I actually run on one of these chips? Yeah, here you go. Foxtail, Brittle Cone, and Sycamore. Okay, so how many qubits does Sycamore have? So here's Sycamore, and here's a little chip. Okay, so there's a variable number of qubits here. It has 53 qubits. Yeah, so basically all of these quantum computers are maxing out at 100 qubits. Like, none of them seem to have more than 100 qubits. Polyairs. What the fuck is a polyair? Probably when you do the measurement and then the measurement is off a little bit. Okay. Does this method provide quantum advantage, like train faster or something? No, this method does not is not better in any way. This is a very simple problem of binary text classification on a very small data set with a very small quantum computer. So this is not doing anything faster or better than classical computers right now. But there's plenty of other papers and things that show you that quantum computers, once they actually get good and once they actually get competitive, will be significantly better than classical computers. So the point of reading this paper is not because this particular paper is going to be the end-all be-all. It's more so because by reading this paper, we've built a little bit of intuition about quantum computers, and now I know a little bit more about what poly-Z are, Hamard, like all of these terms now, ansats. Now when I read those, I actually kind of have a little bit more of an idea about what the fuck I'm actually looking at, versus before reading this paper, I could not told you what a quantum ansatz was. Okay, but so now they keep going, and now they're basically going to carry out some numerical simulations, and then evaluate its performance on binary text classification. In order to demonstrate the performance of our proposed QSAN, we have conducted numerical experiments on public data sets where the quantum part was accomplished via classical simulation. So they didn't even run this on a real quantum computer. They just simulated it, which actually seems like what Amazon Bracket is. It's basically simulated quantum computers. I bet you, I don't know the actual numbers, but I bet you the overwhelming majority of all quantum papers and quantum algorithms are done entirely in simulation. I bet you that very, very few things are ever run on these quantum computers just because they're so big and so expensive. Better performance comparing it with syntactic analysis-based quantum model, so some other quantum algo. Classic self-attention neural network. The fuck is a classic self-attention neural network? You mean a transformer? What do you mean? Yelp. Okay, so these are the public sentiment analysis data sets. So they have Yelp, IBM, and Amazon. That's the data sets that they're going to be training and evaluating on. We then show the reasonableness of our particular quantum self-attention GPQSA via visualization of self-attention coefficients. Finally, the noisy experiments are performed to show the robustness to noisy quantum channels. Okay, so then they're going to show that if you mess with the quantum states and add a little bit of noise, that you still get the correct answer. All the simulations and optimizations are implemented in Paddle Quantum via Paddle deep learning platform. Paddle is the Chinese deep learning framework. So I guess it makes sense that Paddle Quantum exists. Here's your hyperparameters. So these learning rates make sense. Those are kind of they're a little bit big, but those are analogous to classical computing learning rates. Here you have the weights for the regularization terms. So either 0 or some small number here. The dimensionality of the actual word tokens is actually quite small. It's 24, 6, 12. The number of layers, I think that's what n is. Or n is the number of qubits, so 2 qubits, 4 qubits, very small. And then this is the query key value d, so the ansatses for these are repeated d times, right? So the ansats, which is basically these rotations that are parameterized by theta, followed with some C0 gates. This part here with the C0 gates is repeated d times, so basically the depth of the quantum layer within the Q, K, and V's. Interesting that all three of them have the same depth, and then you're using a different depth for the encoder. The encoder operator is what converts your classic data into these superposition states. Only has a depth of 1. The 2 simple synthetic datasets we employed come directly from 40, which are named as MC and RP. Okay, so 17 words and 130 dataset. Look at that dataset size, dude. That is 115 words, 105 sentences. These are tiny. These are tiny little datasets. With 4 words, dude. This one has 4 words. Sentiment label. The contained 1,000. Okay, a little bit bigger, a little bit. 0 for negative, 1 for positive. So this is the binary classification here. Each sequence contains several to dozens of words. Oh, shit, dude. How about that for some context length right there? Several to dozen words. Okay, single self-attention layer. We also perform the most straightforward, averaging directly the embedded vectors, followed by a fully connected, which we call the naive. Okay, so this is their quote-unquote classical self-attention neural network. It's basically just a fully connected layer with an average. I don't know what the fuck that means. Is that how they managed to do backprop? Because they never actually used quantum computers? They don't explain the backprop. They say they explain it in the appendices. So let's actually see. Analytical gradients. We give the stochastic analytical partition gradients of the loss function with regard to this parameters, right? So you want the partial derivatives of each of the parameters in your neural net in order to perform gradient descent, right? Like, the reason you can machine learn a neural net is because I can, if I take in the output of my loss function, right, and I trace that backwards, I can say, okay, well, how much of that loss function was because of this neuron, and 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 because all of this is differentiable, I can go all the way back to the very first neurons in the neural net and say, okay, this is how much I need to change the weight of this neuron here in order to get the answer that I should have gotten for my loss function, right? So that chain rule and that backpropagation is how you can actually change the values of neurons in a classic neural network. But my question is more, okay, I can see how they're doing that for the little head, which is classical, but how are they getting these partial derivatives to go back into the quantum layers? Okay, so let's see what their explanation of that is. We consider the parameters in the last quantum self-attention neural network layers, okay, and the final fully connected layer, WB. So these are the easy ones. These are the ones that I don't know how they did it. Can be evaluated in a similar way, updated through backpropagation. Given the M data sample, we omit M, okay. So the partial derivative of the loss with respect to W, that's easy. The partial derivative of the loss with respect to the bias, that's easy. Okay, but now how are you getting this? This is the hard part. The partial derivative of the loss with respect to the parameters of the value quantum self-attention layer. Here is the chain rule. So chain rule, chain rule, chain rule, chain rule, chain rule. This shit is going to be weird. More chain rule. They did some magic here. So here there's a delta function. Is it, can you just chain rule all the way back? Is there no reason? Am I being unreasonable by thinking you can't just chain rule all the way back? The last three could be evaluated differently via the parameter shift rule. God. Okay, so the derivative, the partial derivative of the output of layer L by this self-attention coefficient times the derivative of the partial derivative of the self-attention coefficient by the Pauli measurement of Q, and then the partial derivative of the Pauli measurement at Q by the parameter at Q. This is the one that I feel like should be hard, because this here, you're doing a quantum measurement. So how do you get the partial derivative of a quantum measurement from the parameter of that quantum layer? Okay, so all of these make sense, but how are they getting this one? And this one. This one is the one. Here we go. Boom. Okay, so the partial derivative of ZQ with respect to this theta, which is the parameter of the rotation inside that, is this. It's 1/2 ZQS plus minus ZQS negative, where ZQS plus minus is equal to this quantum state, complex conjugate quantum state, UQ plus minus Z UQ transpose plus minus. And then UQ plus minus is theta plus minus pi over 2. In order to derive the partial derivatives, we also need the following. Okay. This is still a little sketchy to me, like this one here. This is how you actually chain rule through the quantum measurement, but they seem pretty casual about it. They don't really seem to have any trouble with it, so it seems like you can seemingly just chain rule through the quantum measurement, which was the only part that I thought might not be differentiable, but it seems like it totally is. And then if you can do that, then you can go all the way back to the very beginning of all the way back to the very first layer, first quantum layer, and you can easily calculate every parameter's gradient. That's awesome. Exactly. It's like one of those moments when you just sit there and you stare for like 10 minutes and you just go like, cool. All right, now to the next thing. Damn. Okay, I mean, if someone can explain this, please let us know, because this is kind of sketch. Let's go back up. All right, where were we at? We were here, where they're basically comparing. They're talking about training. All the encoders have the same qubit number and constructed, easily implementable, little typo there, on NISQ devices. This is actual quantum computers. Assuming the n qubit encoder ansatz has decoder layers, we could set the dimension of the input vectors as this. The depth of the query are not set to the same and are at most the polynomial size of the qubit number n. The actual hyperparameter settings are concluding in table 1. That's the one we read up here. In addition, we choose z1 all the way to n, x all the way to n, y all the way to n as the poly observables. For example, it is just required 3 n observables when d encoder equals 1. However, if d encoder is greater than 1, we should also choose 2 qubit observables, z12 and z23. Okay, so these poly observables change depending on the number of qubits, right? And if you're encoding into just 1, then you only need 1. 1x, 1y, and 1z. So that's where the n is coming from. All the ansats and weights are initialized from a Gaussian distribution with 0 mean. All right, there we go. Now we know. So here in the algorithm, they said we're gonna initialize the weights and bias of this little final head here with a Gaussian. But I was like, what are they initializing the parameters of this to? And they're telling us right here. So they've told us all the ansatz parameters, which are the ones that we're going to learn, are initialized from a Gaussian with a mean 0 and a standard deviation of 0.01. This is kind of weird because the ansatz parameters are defining a rotation, right? If you guys remember, up here, the ansatz parameters theta, what they're defining are rotations in the x and y axes of the qubit state. So if you're initializing these as 0 with a standard Gaussian centered on 0 with a standard deviation of 0.01, what it means is that when you start off, most of the values here are going to be 0. So you're just rotating by a very tiny amount in x, rotating by a very tiny amount in y, and a lot of times just rotating by 0. So it's kind of weird. I would have thought that you would have wanted maybe like a uniform distribution over negative pi over 2 and pi over 2 or something like that. You know, like you would have wanted them to be a little bit more intense in terms of these rotation angles, but it's kind of interesting that they initialize it to basically 0. Okay. Sorry, I'm like scrolling all over the place here, guys. The ansat parameters are not here. The ansatz parameters are not initialized uniformly. Okay. Wow. Interesting that they basically were like, hey, that thing that you just thought of, hey, by the way, this is not why we're going to do it. Mainly due to the residual. Okay. During the optimization, we use the atom optimizer and we repeat the experiment 9 times with different parameter initializations to collect the average accuracy. Okay, so they use a bunch of different random seeds for the initialization of the weights. I guess that makes sense. It'd be interesting to see what the fluctuations are. Test accuracy of QSAN compared to CS-SAN. This is the classical self-attention. Number of params, so 49 parameters, very few parameters for this tiny little quantum neural network, and the kind of classical analog here is 785 parameters, which is obviously also very tiny. This is just literally parameters. We're not talking about millions of parameters. The variance here is higher, which is more interesting, right? So it's kind of on par with this tiny classical one, but interestingly, the classical neural network is a lot more robust to initialization of the weights, right? Versus the quantum self-attention neural network is much more sensitive to the initialization of the weights. If you use 9 different seeds and you get different values for those thetas, which represent rotations, you're actually going to get a bigger spread which is kind of cool. What else? Training accuracy as well as DiscoCat. 100% training accuracy, so it's overfit. That's good to know. 100% task accuracy, that's weird. I guess if you have a very, very tiny data set, then 100% test accuracy is achievable, but that still means weird. Like if I see a 100% test accuracy, I immediately suspect that I'm training on the test. You know, this is a common mistake. If you fuck up the way that you split your data set into train and test, and you think that you're training on train, but really you're training on the combination of train and test, you can get to 100% test accuracy. But so if you see 100% test accuracy, generally that's not a good thing. Yeah, this is more what you should see here. 95% and then 67%. So 95% train, 67% test. Results on MC and RP tasks. DiscoCat, this is like the best name. The powerful ability of QSAN for binary text classification. I don't know if it's powerful. I feel like that's just a very easy problem. Parameters in the encoder are not counted as they could be replaced by fixed representations such as pre-trained word embeddings. Okay, that's interesting. You could use classical encoder. We get a higher training accuracy but a slightly lower test accuracy. It's mainly because there's a massive bias between the training and the test set. And then here they have their results on the sentence tasks. And here they're showing you the weights, the attention weights, self-attention coefficients. And basically this is telling you which words are related to each other words. So obviously not... Boo. Come here. Come here. Come here. Come say hi to the stream. Come say hi. Kitty. Little kitty, say hi. Okay. Obviously the word not and nasty are related in this sentence. I'm starting to lose steam, guys. QSAN could have a potential advantage for text classification. I don't know about that. I think that you can't really make any big conclusions out of this. It's too small, data set too small, problem too simple. Demonstrate the reasonableness of the Gaussian projected self-attention. In figure 4, we visualize the average self-attention coefficients. Noisy experimental results. So then they, due to the limitations of near-term quantum computers, aka quantum computers that we can actually build, we add experiments with noisy quantum circuits. So you add some amount of noise to the state. Okay, so here you have your basic bricks here. You have your U operators for the key, query, and values. You have your encoder U, and I guess they add depolarizing channels. The fuck is that? The amplitude damping channels are added in the same way. Noise-free, depolarized, and amplitude dampened. So you can see how here the noise level, as it increases, the test accuracy I guess here they're saying the test accuracy is between 0.82 and 0.86 for a noise level of 0, which is noise-free. And then as you increase the noise, the spread of the accuracy goes a little bit wider, but really I guess what they're most excited about is the fact that it doesn't kind of grow out of control and that you still have a reasonable amount of accuracy despite a high amount of noise, right? And if what they're trying to say is that near-term quantum computers need to be robust to noise, then this plot here kind of shows that. The absence of a notable decrease of accuracy implies the noise resilience attribute of QSAN. And this is the actual nature of the noise here. The Krauss operator. Isn't that just the outer product of a bra and a ket? Or a ket and a bra? Here, rho for a pure quantum state and p denotes the noise level. Okay, so P is the noise. A regular way to analyze the effect of quantum noise, we add these single qubit noisy channels to the final circuit to represent the whole system noise. All right, we're almost at the end here, guys. Discussions. We have proposed a quantum self-attention neural network by introducing the self-attention mechanism to quantum-level quantum neural networks. Specifically, the adopted Gaussian projected quantum self-attention exploits the exponentially large quantum Hilbert space as the quantum feature space, making QSAN have the potential advantage of mining some hidden correlations between words that are difficult to dig out classically. I love the use of mining analogies. Numerical results show that QSAN outperforms the best-known QNLP method on a simple classical self-attention neural network. I would say that probably shouldn't read into that too much. Moreover, using only shallow quantum circuits and Pauli measurements, QSAN can be easily implemented on near-term quantum devices and is noise-resilient. Noise-resilient and implementable on near-term quantum devices. We believe this attempt to combine self-attention and quantum neural networks would open up new avenues for QNLP as well as QML. More advanced techniques such as positional encoding, that's right, there was no positional encoding here and no multi-head attention, can be employed in quantum neural networks for generative models and other more complicated tasks. The whole reason you have multi-head attention, though, is because you can parallelize it across the fact that a GPU can do things in parallel. So, like, I don't know if quantum computers have the same thing, right? Like, we're not even at the point of a quantum CPU, let alone a quantum GPU, right? Like, what would a quantum chip that's optimized for parallel computations look like? I don't know. We'd like to thank some people for helpful discussions. This was China Scholarship Council. So Chinese government money and Australian government money. Okay. Cool. That's pretty much it, guys. My brain is fried here. If you guys have gotten here to the end, you guys are absolute warriors, you know? Props to making it to the end. Props to surviving. Let's see if we can summarize this. Take a big sip of yerba mate and then I'll summarize this. All right. And you know this. I don't know this at all, man. I feel like a little bit more comfortable now with quantum machine learning, but it still feels like some dark art shit. Quantum self-attention neural networks for text classification. So today we read a paper coming out of Baidu Research and University of Technology Sydney, so Australian and Chinese research group, that implemented a self-attention mechanism for text classification. So very simple type of text classification, just binary classification. The sentences they were using were also like really short and very small. So kind of like a CFAR10, like MNIST kind of result. You know, we're not pushing the state of the art here. We're just basically showing that you can implement something that looks like self-attention in a quantum computer. So another thing about this paper is that they are implementing this on what they call near-term quantum computers, or noisy intermediate scale quantum computers, which are, in the world of quantum computers, you can do everything in simulation and pretend you're working on a quantum computer that's perfect, but we don't have those in real life. The quantum computers that we have in real life have somewhere on the order of 100 qubits, and they are very noisy. So you have to be robust to noise, and you have to have something that works with 100 qubits. So they limit themselves to that type of hardware. So they're like, okay, only roughly 100 qubits, and it has to work with the noise, which they do end up showing that they are robust to noise. What else? Their self-attention mechanism is, or their self-attention neural network is actually it's not just entirely quantum, it's composed of both quantum pieces and classical pieces. Classical pieces refer to kind of classical computers, bits, just zeros and ones. So the quantum part is an encoder, and they call these ansats. So a quantum ansats is basically a quantum circuit, and They have quantum ansatz for the encoder, which takes your actual words, in this case, or tokens, if you want to call them that. And they also have quantum ansatses for the keys, the queries, and the values, which are the three basic components of a self-attention mechanism in a normal self-attention mechanism. So the keys and the queries you're using to get these self-attention coefficients, which you're then using to basically figure out how much of the value you're passing on to the next layer. And then you have multiple layers of this, which is analogous to classical classical self-attentions. Another thing that they steal from or not, they don't steal, but they're inspired from and that they reuse from classical self-attention mechanism is this residual connection. So they also have a residual connection, which allows gradients to flow through multiple layers. What else? We learned that there's a couple different terms here from quantum computing that are interesting. We have operators, the notion of these operators that operate on quantum states. Quantum states are superpositions of 0 and 1, right? And the superposition there refers to that there's a probability that it's 0 and there's a probability that it's 1, and it's both of those at the same time. And until you measure it, it's both of them. But then once you measure it, it collapses and it becomes a single state. So these operators, such as the Hamard gate, will put it into a quantum superposition, and these Pauli operators are basically rotations amongst the x, y, and z. And you can think of those rotations amongst x, y, and z as kind of like whenever people talk about imaginary numbers, they talk about the real numbers being on x and the imaginary being on y. So an imaginary number is a combination of, is some vector in this real and imaginary plane, or whatever you want to call it. You could think of kind of an analogous situation here where these rotations are on the x, y, and z of the two states of the quantum state, or the two parts of the quantum state. Okay, what else? The self-attention layer is basically they encode the quantum state. So you have some quantum state here initialized at 0, and you have n qubits. You have the Hamard operator to put them in superposition, and then you encode your classical input data into an operator here, this uEncode, and that uEncode modifies the quantum state. And then they do some fancy shit here with the Pauli Z measurements, which honestly I still didn't really understand. Here's your residual connection. And one of the tricky things that they do here is they take the actual measured output of the queries and the keys and they put it into a Gaussian. And they kind of say that, hey, you could have done this with some other things, but we just chose a Gaussian because it's well studied and because we like it. So there's that. In terms of the actual ansats, so this little brick here, right, where the actual quantum computation happens, and what we learned here is that this little speed dial means they measure. So here they're collapsing the quantum state. So everything to the right of here is classical state, and everything from here to here is a quantum state. So one thing that we learned is that in these ansats, which are these little quantum circuits, they are basically composing a bunch of rotations by some angles theta. So they're saying, okay, rotate x by theta, right, where they're using that Pauli X operator to basically define what that rotation is, but it's parameterized. So it's a rotation by some theta, and these thetas are the actual parameters. So in a classic neural network, the parameters that you're changing are the weights of a neuron like this, right? So you're using backpropagation and then gradient descent to change the values of these neuron weights. In a quantum ansats, what you're changing is the angles of these rotation operators. And these rotation operators are combined with these CNOT gates, and what these CNOT gates are doing is they're basically entangling these qubits. So you're rotating the quantum states, and then you're entangling them, and then rotating them again. So you're creating kind of this big mess of connectivity, which is actually kind of similar to what you're doing in an actual classical neural network, where you're kind of creating this mess of connectivity where everything is kind of related to everything, so that they kind of like are entangled, even though the word entangled doesn't necessarily make sense in a classical context. But that's the ansats, and then they have ansatses actually are, there's multiple repeating blocks of this C0 gates and rotations. Okay, so once they create this quantum self-attention layer, they put a bunch of those layers together. So here you can see how they have multiple quantum self-attention layers. The input here is going to be your sentence, and then the output here is going to be a classification. So they were doing binary classification for sentiment. So is this sentence negative or positive? And they take their quantum self-attention neural network, and then they add a little head on top of it. So this little part here is just a standard fully connected little neural network that just outputs a prediction on the category. And then they backpropagate, and it turns out you can just basically backpropagate through quantum self-attention layers, including these C0 gates and including these rotation operation and including these measurement operations. So I thought there would be some complexity there, but there isn't. And apparently you can just simply chain rule and backpropagate all the way through all these quantum self-attention layers and change all the little values of these thetas such that you eventually get a stack of quantum self-attention layers combined with a little neural network fully connected head that gives you a working classification model. The loss function that they use is pretty standard, just a kind of a mean squared error with some regularizations. What else? Here's the actual algorithm. They're initializing the parameters of these rotation to actually a bunch of zeros, which is interesting. The ansats parameters, which are those rotations, are all initialized to basically 0 with a little bit of variance. They then go to show this is very tiny, so the number of qubits is tiny, the depth of these ansatses is tiny, the total amount of the dimensionality of the input tokens is also tiny. So everything is very small in this paper. Like look at these, like 1,000 sequences, 115 words. Like these are very, very tiny data sets. This is just basically a proof of concept. But they get pretty good results. So they compare their technique to comparatively tiny. So they call this a classical self. They're using way more parameters than that. But they get results and they're good and they can actually learn something. So kind of cool. And then they show that it's robust to noise. So if you add extra noise into these quantum states, it still manages to get the right answer, or get the accuracy is still fine, which means that if you were doing this on a real quantum computer and half of your quantum bits were noisy, you would still get the right answer. That's basically it. There is a paper called Chain Rules for Quantum Channels. Maybe that's the next one we read. John Egan, you have been the one on the stream who seems to have the most intuition on quantum. Probably because I didn't still have the quantum mental intuition of this quantum computing and what the fuck was happening. Yeah, don't worry about it. It's hard for me too. I'm definitely still confused about a bunch of these things. But maybe one thing that the surprising effectiveness of random CNNs. This is something that I thought. I've brought this paper up before, but this might not even be the one that I want. But basically, in one of these papers, they showed that you could initialize a convnet to basically garbage and then put a little classification head on top of it, and it still works. So I wonder if what's happening here is basically the same shit, where it doesn't really matter what these let me scroll up. It doesn't really matter what the fuck these quantum self-attention layers are doing. All the classification intelligence is really coming from here, right? So that's something that I don't know. I don't think they answered it, but I would have loved to see, like, okay, if you just have this in a completely untrained state. So let's say you freeze this, you freeze all the parameters of this quantum brick right here, and then you only train this. How high of a test accuracy do you get? Because I suspect it might be suspiciously high, you know? So sometimes you can convince yourself that this thing here is actually doing something, but really it's the head that's doing most of the intelligence. But they did not do that experiment, so my random prediction and question will never be answered. Cool, that was pretty much it. We also figured out that there's this, what was this? Yeah, this thing. This thing is pretty cool. So we found this website, Quantum Inspire, where you can basically create little quantum circuits. So here we go. We can also HQ0. So we can Hamard gate the qubit, then C-naught it, then measure this qubit, and then Hamard gate it again. So there's seemingly like little websites like this where you can get an idea of what every single gate is in these quantum computers, and you can simulate your own little quantum computers, which is pretty cool. But that's it, guys. I gotta head out. This stream is already way too long. Thank you, John. Thank you, Ed. Thank you, Joseph. Thank you, Deadly Data. Thank you, Luke. Thank you, Riddell. Thank you, Christopher, Navjot, John Egan, Luke, Joseph, Daniel. Pretty much everybody here. Thanks for the questions. Thanks for going on this quantum journey with me. Hopefully you got something out of it. Hopefully you learned a little bit. Maybe not. John Egan, it sounds like you kind of already know what the fuck is going on here. Maybe you need to drop in the Discord channel and tell us more about quantum computers. But hopefully that was interesting, and I'll see you guys tomorrow. Peace.